You're blind when you look into the sun and want to see something else, read the book afterwards. It takes some time for the eye to adjust until you can read it, because the sun is so bright. The radio frequency pulse is so strong that we cannot measure the beginning properly. But you can then play the trick with the phase correction and see the beginning of that signal.
So phase correction is actually on FID?
Well, you can do it on both. You can do it either on the FID or you can do it on the spectrum. It's usually done in the frequency domain after the Fourier transformation. And then the phase itself is a linear function that can work out when one does the math. It has a constant phase term, which you can also correct in the FID. And it has a frequency-dependent term, which really relates to the dead time. The frequency-dependent part, proportional to frequency, is really something that derives directly from the dead time. And the constant term derives from the time it takes for the signal to walk half.
So these are two origins of the phase of this phase term. Okay. Now, start getting a bit more complicated. We have, if we are in the rotating quarter.
So we are the red bicycle rider. We're exactly on this, with the same frequency as our radio frequency field. But the yellow bicycle rider, who is slightly faster, is the magnetization that we are observing. Now suppose we want to do a 90-degree pulse and rotate the magnetization from the z direction bicycle rider. Now, in practical terms, that means you want to excite the whole spectrum and get the magnetization from all components, the phenyl, the aromatic components and the aliphatic components, and rotate those that have different frequencies all into the transverse plane to measure them. You need a bandwidth of your excitation. If it's just on one particular frequency, you do, let's say, only for the methyl groups, but not for the methylenes and the aromatics. So only for the red bicycle rider, but not for the yellow one. You need, and the question is, what does the magnetization do? Well, you actually have this off-resonance field, which comes from the different frequencies. The yellow bicycle rider has a small precession frequency in the rotating frame, so there's a residual magnetic field. That's his magnetic field. That's B off. This is the magnetic field of the yellow bicycle rider, the rotating frame. B1 is the magnetic field that is generated by the transmitter. Now the spins don't know if the magnetic field comes from the off-resonance field, if it comes from the transmitter, where does it come from? The spins take the magnetic field that they see, the sum of all magnetic fields that arrive at the site of the spin. The sum is the vector sum, because the off-resonance field is in the z direction. The excitation field is somewhere in the transverse plane, let's say in the y direction. So the vector sum is this one. We call it the effective field. And the spins rotate around the effective field. Now what happens when your B1 field is very small? You make that arrow very short. Then the effective field points along that direction. You can see there's a critical angle at which you cannot rotate the field, the magnetization, anymore into the transverse plane. if you rotate, if your effective field goes along a 45-degree axis, you need a 180-degree pulse to rotate the spins from the Z direction to the Y direction. If your effective field is close to the Z direction, you cannot rotate them at all into the transverse plane. But if your effective field is exactly along the Y direction, you can beautifully do a 90-degree pulse and rotate them into the XY plane. And what determines which direction the effective field points is the magnitude of the V1 field. That means how strong is your transmitter? How short is your 90-degree pulse? So especially when you're at high fields, you spend a lot of money, you're a rich person, you buy yourself a 1 gigahertz spectrometer. Most people dream of that to have beautiful spectra. They need a very powerful transmitter because your frequency range is very large. For carbon-13, 250 dBm for carbon-13 or 1 gigahertz, you can figure out what frequency range that is. And you will quickly learn that the electronics is very hard to get, so do a 90-degree pulse, a proper 90-degree pulse for the whole width of the carbon-13 spectrum. So having a high magnetic field makes you proud, but it may cause other difficulties. It just shifts the set of difficulties, and you have to deal with frequency-selective pulses. Actually, the fact of making V1 short is used in magnetic resonance imaging to select slices of a three-dimensional object, or even in NMR spectroscopy to say I want to only excite the aromatic region and not the aliphatic region in the spectrum. Then I use a weak transmitter. I use a pulse with a small V1 field, and I set my excitation frequency in the proper way that the off-resonance field has the right value, and then I can do a selective excitation.
So typically we use 10 microsecond or...
yes, but that's done for non-selective excitation. Then V1 is big enough so that you can excite the whole spectral width.
But you mean if it goes down to 8 microseconds or 7 microseconds, it will make a difference?
No, then you just use more radio frequency pulse, you get power, and you have a larger bandwidth that you excite, in fact larger than you ever need. But if you make it too long, if you go from 20 microseconds to 1 millisecond, then you will start having selective excitation. And that gives artifacts, and the lines at the end, right or left of your spectrum, never become too small. And then the quantitative analysis, you cannot do it anymore. The integration will give you wrong numbers of the number of spins that you analyze. Okay, so the next thing now we need to discuss is relaxation. We've discussed how we excite the spins. We have learned in one of the previous slides that we have a time it takes for the magnetization to build up when we put the sample into the magnet until we have longitudinal magnetization. And then we have also seen when we tip over the magnetization, when it oscillates and decays, at the decay time, we call the transverse relaxation time T2. And I'll discuss there are two relaxation times. One that relates to magnetic field inhomogeneity, and another one which I didn't explain. Now I need to explain what I haven't. So, we go back to bicycle riders. I like to ride a bicycle. This is, suppose the different magnetization components of, it could be chemical shift, or it could be different positions of your solute in the sample tube, where the magnetic field is slightly different. So each of them points to one of the bicycle riders, different magnetization components. And then you do the 90-degree pulse, and that means you tell the bicycle riders you start your race around the circle. The riders go around the circle. Some go faster, because let's say they are the aromatics, they have a higher frequency. Or they sit in a part of a sample tube where the magnetic field is slightly higher, so their frequency is higher. And the aliphatics are the slow guys. Okay, so they go slow. And then after a while they spread around the circle, and they're the sum magnetization is 0. The vector sum of all the components from the center to the bicycle riders is 0. So it means your NMR signal has disappeared, you don't see it anymore. And the second pulse is a 180-degree pulse. What the 180-degree pulse does is actually explained here, but I will use a is an analogy saying that the 180-degree pulse is equivalent to telling the bicycle riders to change directions and go back. So now you see you have the same distribution here, but at this moment now they all point to the different directions. They all change their direction. They still go with the same speed. What happens? The fast guys are now the ones behind, and the slow guys are the ones in front. And so if they go with the same speed, they all come back at the same time, which we call after the echo time at the starting line, but pointing in the different direction. This is what we call an echo. And the echo actually has been discovered by Irvin Hahn in 1949. I mentioned yesterday, Irvin Hahn unfortunately passed away this year, a few months ago. And his pulse sequence, he was just fortunate to discover it. Was ready for discovery, and he was a lucky guy who was able to discover it. And this is how he describes it himself. So you do a 90-degree pulse. It is you put the magnetization, start the magnetization components. First you have Z magnetization. You do a 90-degree pulse along the x-axis, so you flip the magnetization over, right-hand rule, button points in the direction of your B1 field, and then you flip by 90 degrees, puts the magnetization along the x direction. And then the magnetization in the rotating frames, some move faster than you, some move slower than you, go right and left, so they spread around. Now we go from 1, 2, 3. This is the next one here. So the magnetization spreads in one way and the other way. I identified two components in color. And then you do a 180-degree pulse along the x direction. The 180-degree pulse means you rotate the whole plate of magnetization components by 180 degrees, which means you exchange red and blue, for example. So that one moves over here, the blue one moves over here. So 180-degree pulse. And now you have this scenario. But the precession direction stays the same. It's slightly different from what I explained with the bicycle riders. The precession direction stays the same, but still, then after a time, the same time it has taken for the magnetization components to run apart, they assemble back along the x direction. And that gives the echo.
So normally, after 90 degrees, we put in y direction. Is there any particular reason?
Yes, there is a particular reason, because it's better in terms of phase and pulse errors that you get. So it's actually, the better explanation is, actually I've done that too. I have a 90-degree y and a 180-degree x. So there's this 90-degree phase shift between the two pulses. You also can do 90 x, 180-degree x, and the echo forms along a different axis. But phase errors accumulate slightly different. There's compensation schemes for not being able to produce exactly 180-degree, 90-degree pulses, and to compensate those, we play with the phases of these pulses. Yes. And there's the second form of an echo that is still used, and we need that later on when we discuss diffusion, for example, is the stimulated echo, that you can break that 180-degree pulse into two 90-degree pulses and have some time in between, and that is what we call a stimulated echo. It first generates a Hahn echo with two 90-degree pulses. Actually, I should mention that the Hahn echo does not require a 90 and a 180-degree pulse. Irvin Hahn used arbitrary pulses and discovered the echo. He didn't even know at that time how to set a 90-degree pulse properly. And so those pulses, any two pulses, radio frequency pulses, strong enough though, will produce an echo. And the same applies for optical echoes, which also Irvin Hahn discovered, and that you use two laser pulses in a nonlinear medium, and then you generate an optical echo, and you use that for information storage. So that's a fundamental discovery of the echo, and it's the basics of MRI. No magnetic resonance imaging method would work unless you use this type of an echo. So this is, has a tremendous impact onto modern society that we have these echoes. So the stimulated echo is another one which allows you here to introduce a waiting time of time t1 to then see two echoes, actually, the Hahn echo and the stimulated echo. We see how far we get. Let me do, before we take the break, address just the multiple echoes. And the multiple echoes are the case that you do a 90, 180 degree pulse, you generate your first echo, and then you add further 180 degree pulses and you generate more echoes. It gives you an echo train. There were 4 people, Gill, who invented that or discovered that and optimized that. This is why it's called the CPMG echo train. So CPMG is something that many people that measure relaxation know, and especially people in the oil industry deal with it every day. This is their way of measuring NMR signals. Because the fact is that the echo peaks, the echo amplitudes, if you connect them, they give you the relaxation decay which you naturally observe in perfectly homogeneous fields. And this tells us that in inhomogeneous fields we can still measure that relaxation decay with a simple CPMG multi-echo sequence. Very fundamental for relaxation studies, for materials analysis, for the physics sort of community of magnetic resonance. In chemistry, people are not so important. They want to measure the free induction decay, homogeneous field, get the spectrum. So we will deal with T1 after the break, and then we deal with spin-spin interactions. Okay? Let's take a break. Yeah, questions, of course.
We have a signal in time domain.
Yes.
So we convert firstly into frequency domain.
We can say
convert it into frequency domain.
Yeah, by the Fourier transformation.
Yeah, by the Fourier transformation. We get 2 frequency, one is negative and another is positive frequency.
Yes.
So negative frequency is useful in NMR or just related to phasor?
Well, it's a matter of the spectral width and the way you set your filter in the electronics. It's better to sit actually in the when your noise runs only from 0 to half the maximum frequency. So you get less noise in your spectrum. But that means you have to acquire real and imaginary part of your rotating magnetization, rotating in the rotating coordinate frame. And otherwise you cannot discriminate positive and negative frequencies. If you observe a linearly polarized or a linear oscillation, a cosine function, that is insensitive to positive and negative frequencies. So you need cosine and sine function to discriminate positive and negative frequencies. So it's for let's say, reasons of signal-to-noise ratio sensitivity that one uses what people call quadrature detection to discriminate positive and negative frequencies. Did that answer your question, or did I bypass it?
Negative frequency is meaningful, or you can define?
Well, it's arbitrary. Negative frequency depends on what frequency you are in your rotating coordinate frame. And the frequency of the rotating coordinate frame is the frequency of your radio frequency excitation. In fact, all the measurements happen in the rotating coordinate frame. It's done by the electronics. So you actually multiply your NMR signal that is at frequency omega 0, the resonance frequency, with the frequency or the sine omega 0 with sine omega RF times t. And that gives you the sum and the difference frequencies. And depending on where you set the radio frequency, that tells you whether you have positive and negative frequencies in these sums and different frequencies of your spectrum. It's just electronics. It's useful to do, but not necessary.
But probably he's asking during the phase correction, the negative will go out. And it will be only the positive that will be visible in the form of signal.
No. Both will stay. Both will stay. If you do the right phase phase correction, you said. No, both. You can do that for positive and negative frequencies. Okay. Other questions? Let's have some tea. Now, suppose some get tired and some eat an energy bomb. Okay? So they will change their speed. And so some will be faster, some will be slower. Then they will not all arrive at the same time. Some will arrive earlier and some will arrive later. Now that means that the total signal, which is a vector sum of the vectors pointing from the center to the bicycle rider, will be shorter. That means the echo will be attenuated if the bicycle riders change their speed while they are riding. Now that's important. If the bicycle riders don't change their speed, that would be the case where we have magnetic field inhomogeneity. One part of the sample has a higher field, the other one has a lower field, and the spins in that part stay where they are, and those in this part of the sample stay where they are. So the precession frequencies never change. That's static magnetic field inhomogeneity. That's the reason for signal attenuation, that is T2 star. It's a signal decay, and you can refocus completely. You get all the bicycle riders back when the spins stay at their position. But you don't get them back if the spins experience, for whatever reason, fluctuating magnetic fields. So something that at random changes. And why would magnetic change randomly for the spins? Well, because the molecules themselves move, they rotate, they're magnetically anisotropic. One molecule passes by another molecule that also has a magnetic field, and then you have, due to the motion of the molecules in the liquid or in the solid, you have fluctuating local magnetic fields that the spins see. So while they are precessing, they sometimes go faster and sometimes go slower. But that is completely at random. That is nothing predictable. So on the way this way and on the way returning, they see different fluctuating fields, and that means there still will be a spread of the bicycle riders at the finishing line, and the echo will be attenuated. And that, from the fluctuating fields, is the true T2. So what people would like to measure, they want to measure the true T2 without magnetic field inhomogeneity, to learn about the local fluctuations of the magnetic field. Because that tells them about the mobility of the molecules, and a soft material will have higher molecular mobility than a rigid material. Or a high viscosity fluid will have lower molecular mobility than a low viscosity fluid. So T2 star, you can say immediately already with that, no, T2 will relate to the viscosity of a fluid. This is what the geophysicists exploit when they want to know what type of fluid is in my rock. Is it oil, or is it water, or is it methane? So they can use T2 for that. And again, also, if, for instance, rubber are cross-linked macromolecules. If the cross-link density is high, then your rubber is very rigid, so it feels more like a solid. If the cross-link density is low, then your rubber is, you can stretch it easily, it's soft. And T2 scales with the cross-link density. In fact, that's something that the rubber industry uses when they produce car tires. They measure NMR to learn about the cross-link density locally in the car tire and optimize the vulcanization of the tire in the tire factory. At least in the R&D departments where they develop the procedures. And in fact, yeah, right. So this is hopefully explains the difference between T2 and T2 star. Repeat again, T2 star is what you have in inhomogeneous fields. You don't want to have it actually. And T2 is what you have in homogeneous fields or inhomogeneous fields, and it is solely due to the fluctuation of local magnetic fields from molecular motion. And there is the physics. It's the molecular motion. That's the physics. And that is impacted by all kinds of things. You know, molecules sit in a small pore, they can move less freely than in a large pore. So pore size you can measure in terms of diffusion, which we'll address later, by similar measurements that basically affect the magnetization decay and gives you pore size distributions which you can nicely determine by NMR. That's something for later.
In normal spectrometers, it is possible to differentiate T2 and T2 star?
Oh, absolutely. You can do, if you can do an echo, you can discriminate T2 and T2 star. T2 would be, where am I? Here, difficulties with moving this. T2 star is the decay of the signal that you observe when you look at the free induction decay. But when you do an echo experiment and then change the echo time, then you observe the T2. T2 star is this one. And T2, where is it? Yeah, maybe this is a better example. If you measure the signal decay in an inhomogeneous field, badly shaped magnet, your signal decays fast, your line is broad. Then you see the blue decay. That's a T2 star decay. If the magnet is perfectly shaped, very homogeneous field, you will see the T2, which is long. But there may be still residual inhomogeneities which you can't churn out because, for whatever reason it doesn't work as well. Then you can do the multi-echo experiment, and that decay is the true T2. There's still effects from diffusion in inhomogeneous fields that could enter if you have liquids. Then you have to take the echo time, that is the time TE between the echoes short enough, or the time between the 180-degree pulses, same, to make that short enough to have no contribution of diffusion to the relaxation signal. But again, this is part of a later lecture. So yes, you can measure that, and the relaxation is usually measured in terms of these of doing echo experiments and looking at the signal decay.
Can it be more reliable to have T2 star?
Pardon?
T2 star, it is taking into consideration the inhomogeneity. T2 star.
Yes, that takes it consists of the true T2 and the field inhomogeneity contribution.
Yeah. So that means T2 star is actually the true value instead of T2 only.
No, you want to measure T2 because, or let's say most people want to measure T2 because that only depends on molecular mobility and motion. And people are asking, what is the mobility? It's the kind of physics aspect of matter, is the molecular mobility. The chemistry is really the chemical shielding, the J-coupling, and so on. And that you can resolve better when you, of course, have a shaped magnet and don't have much T2 stuff, only the true T2. So the line width is determined by true T2. Because that's explained here. When you do the Fourier transformation of these signals, then the red signal gives you a narrow line because it's long at the time domain, which means it's short, and something that's short and narrow at the time domain gives you a broad signal in the frequency domain. So that fast decay gives you a wide and narrow line, actually low amplitude because the integral is the same for both cases, and a narrow line with high resolution when you have the long signal. Okay, so that's the T2 part. I will continue with T1 relaxation when we have revisited the rotating coordinate frame. And that probably takes a little bit more time. Let's do that. Here is one. Let's look at the magnetization. First of all, at the precessing magnetization. We have some magnetization vector here, and this is the rotating frame, x, y, z. Our magnetic field goes into this direction, and the magnetization precesses after some pulse in this direction, and precesses with frequency omega 0 equals 2 pi mu 0. Okay. So this is, just one magnetization vector doing its rotation. Now you want to couple with a magnetic field. You want to interact with that magnet by bringing in an oscillating field. So that oscillating field should sort of follow that rotation in the plane perpendicular to the z direction. So it also has to do this motion along with it. If it does it in the opposite direction, it's out of resonance. You want to move along with the magnetization to couple to it. So you want to have a magnetic field, x, y, z, which also oscillates with the frequency. And this now is a V1 vector, which rotates around the z-axis with the frequency of the transmitter. To be on resonance, you want to have omega transmitter equals omega 0. So you need the same frequency. You generate that with a radio frequency coil by taking a, what do we do this? You build your, you have your sample in a radio frequency coil, and that produces an oscillating magnetic field B1. What do we have? Cosine omega transmitter times T. So that's what your electronics gives you. And that you decompose this magnetic field, which oscillates in that direction, you decompose into two rotating fields, one rotating this way and one rotating this way, of amplitude V1, of amplitude V1, and this is 2V1. So you take the sum of these two fields, and you say the perpendicular components will always cancel, and only these components in that direction or this direction will add up when you do this type of a rotation. So that's the rotation you need to do. I hope I do this right, this is complicated. And this is the explanation how the signal adds up according to Euler's formula. So that, in other words, that magnetic field which oscillates linearly, this field, this is the same, this field is the same as this one, is decomposed in one that rotates this way, and one rotates the other way. So this one here rotates in the same direction as the spins, and can couple to the spins. That one doesn't. And in the rotating frame, it just means that you rotate with that magnetic field. You just basically sit as an observer on this magnetic field. And then you vary the frequency omega transmitter. And this would be in the rotating frame. No, the laboratory frame is minus omega transmitter. So you vary that frequency until you are exactly matched with with this V0 field of the magnetization. So your transmitter field, this field corresponding now to that field, has to match that frequency. Omega transmitter has to be omega 0. And then you are on resonance. If you're a little bit off resonance, you have a mismatch. Omega equals omega transmitter minus omega 0. And that mismatch gives rise to a residual magnetic field that still appears. You're exactly on resonance, your magnetization doesn't seem to rotate, so there doesn't seem to be a magnetic field. If you're off resonance, if you have a mismatch of your transmitter frequency, remember you're always sitting on the V1 field of the transmitter. This is your observer position. If there's a mismatch, then you have a residual frequency, and that residual frequency is gamma V of resonance. Does that make it a little bit clearer? Not everybody is happy with it. It's a complicated thing. But you do have the lecture notes, and you should look it up. And if by tomorrow morning you say you still need to repeat that, then let's repeat it a third time. There's no harm in that. I told you I also needed days to understand this. So if you have a little bit difficulties now, it's okay. And but it takes also the effort to reflect about it and to understand it. Yeah? Okay. So let's move on to the way we have looked at how to measure T2, and now let's figure out how to measure T1. And T1 is the longitudinal relaxation time. It's the time when you put a sample that has no magnetization, you put into the magnet and you want to wait, when can I start measuring, when is my thermodynamic equilibrium, when has that been reached, when have the spins aligned parallel or anti-parallel to the magnetic field, according to the Boltzmann distribution. And this is, since this requires an energy exchange from the spins to the surroundings, energy transfer takes time. And this time constant for to reach equilibrium and exchange the energy between the surroundings, which we call the lattice, and the spins, that's a spin lattice relaxation time, or longitudinal relaxation time, because it concerns the magnetization in direction of the magnetic field. So what one does, there are two ways of measuring. The first way is you put your sample in the magnet and you don't worry how long it's sitting in there if magnetization has built up. You just bang it with many radio frequency pulses. And this is typically several 90-degree pulses where you decrease the distance and the time from one pulse to the next, from pulse to pulse. So you take something like 4 or 5 pulses and always half that distance, half the time separation, and then after 4 or 5 pulses the magnetization is gone. There's no longitudinal magnetization left. It's distributed randomly in space. And then you just wait. You wait until Z magnetization along the Z-axis builds up by one relaxation. But you can't measure it. You can only measure transverse relaxation. So what you do is that you then do a 90-degree pulse afterwards and convert whatever is along the Z-axis, the magnetization that has built up along the Z-axis.
Flip it over into transverse magnetization, have it rotate, and measure the free induction. So the signal then is, this is your acquired signal, and the amplitude of the acquired signal is determined by the Z magnetization before the 90-degree pulse. It's called saturation recovery. And then you repeat the measurement with a different recovery time, and point by point can sample the build-up time. So it's an indirect detection of the magnetization build-up along the Z direction. It requires several measurements. It's actually the original, the idea behind two-dimensional NMR spectroscopy. People haven't thought about it that way. And now people have recognized that's a two-dimensional experiment. You measure T1 in this time, and you measure the signal decay. So your signal build-up is T1, signal decay is T2. You measure a T1, T2 correlation experiment. And you will see that's very important in geophysics. It can do a lot of physics of forest mediated if you do from that type of experiment by reading it as a two-dimensional experiment. Now the other way of performing the experiment is say you build up longitudinal magnetization and then you take a 180-degree pulse and flip it over into the minus Z direction. And then from there on you say, let's wait and see how the magnetization returns along the Z-axis. So the waiting time T0 is that you vary, the signal builds up, and at each increment of T0, you measure, you apply a 90-degree pulse and measure the free injection decay. Again, you see the build up step by step, one different T0s, here is one, there is one, there is one, different T0 times. You repeat the experiment n times and measure from the signal amplitude indirectly that build up. And that's again a way of scanning, of recording the T1 build-up time. And again, you may ask, well, what did I learn from doing that? And the answer is the same as with T2. There's a slightly different theory behind it. You also learn about molecular motion, but you learn about molecular motion on different time scales than T2. With T2, you're particularly sensitive to slow motion. And with T1, you're sensitive to faster motion. So they're complementary, and they're not exactly the same. And typically, T1 is longer than T2. And for liquids that have low viscosity, T1 is equal to T2. That's a limiting case. In many solids, you have T1 being much longer than T2. And that is because there are all kinds of spin-spin interactions that make T2 very short. And this is a topic we will address in the remaining part of this course, of this lecture. But let me first again go to ways of measuring resonance, and I come back to my example with music. And I've shown you two clips from piano music here and from violin sheet music there. And by just looking at it without being a musician, you may say, probably if you had to learn an instrument and you don't have much time, which one would you learn? Probably the one that has less notes, right? Because it's easier to play. It's not really true that the violin is easy to play, but at least from the technology of the music, it suggests that this is easier to play. And these are forced oscillations. You play one note after the other with the violin. But with the piano, you have all your fingers and you can play 10 or I don't know how many, 1, 2, 3, 4 notes at a time. This is more difficult. You have to coordinate much better in your brain, what note to play. And this is the pulsed excitation. So this is more versatile. And that is why pulsed excitation is used in NMR. And the other, where am I? Here. Oh yeah. And this is sort of the three different cases that we have. We have the violin player. We have the piano player where you can play 3 notes at a time here in this case. Or the third one is noise excitation. You take a random radio frequency field and do your NMR, measure your NMR response. And then it looks like this, like regular noise. Why would you ever want to measure a signal like that? This is the most crazy way to measure spectra. And yet, it is the basis of Fourier infrared spectroscopy. This is a machine where you put your sound on, press the button, get the spectrum. And nobody noticed it. You do probably the most complicated one of measuring noise. You have to do an auto or a cross-correlation functional excitation response to get your signal, which you then Fourier transform. We call it an interferogram that you measure. This is nothing but the autocorrelation function of your signal. And from that you derive the Fourier infrared spectrum. People can do the same thing with nuclear magnetic resonance. And I've plotted for you the different measurement methods over here. You have the sine wave excitation, which you take the bow and excite at one frequency, and then you measure how big is the NMR response, no resonance. And eventually when you change the frequency, it comes to resonance and you see it, and then you run out of resonance. It takes forever to measure spectrum because you go step by step through all the different frequencies and see if there's a resonance. If you do the pulsed excitation, it's an infinity short pulse. You see the free induction decay or the impulse response. You do the Fourier transformation now as a decay for your simplicity and excitation, you get the spectrum. It's a bit more complicated with the data processing. This is why it only became possible after having discovered the Fourier transformation, having computers available in the 1960s. And this is the case for noise excitation. This is binary random noise, very complicated, that's a signal response. But you compare the two, and the comparison tells you get the free induction effect. And the comparison, the mathematical word for comparison is cross-correlation or off-correlation. That means comparison. In colloquial terms, we say compare. In mathematical terms, we say autocorrelation cross-correlation. And that's exactly how then the Fourier induction decay is derived from the comparison of these two signals. Fourier transformation will be the spectrum. And the microphone interferometer does this comparison in an analog fashion. That's all it does. That's what an interferometer does. And the output of the interferometer, that is the interferogram or the free induction decay. So we are nearly through with this chapter. And there are 2 slides left, and one refers to imaging. And the way we've seen how we can encode the spectrum, measure spectra. And an image actually is reconstructed from spectra measured in a magnetic field, B, that varies linearly over position X. Now we go away from the constant homogeneous field and say, let's make the field linear dependent. And we know that the frequency, NMR frequency, is proportional to this fundamental equation, omega equals gamma times B. The resonance frequency is proportional to the strength of the magnetic field. So it means if we have a low resonance frequency here, then we have a low frequency or a low magnetic field here, we have a low frequency variable signal. If we have a high field at this point, we have a high frequency variable signal. And all we have to know now, how much is the signal, what's the signal amplitude? It depends on the number of spins we have at that particular strength of the magnetic field. If that's our object, the 2-dimensional, we have a lot of spins here, and we have a lot of spins at that field strength. Fewer spins here. So many spins here, few spins here, the projection is half of an ellipse, what we see. And here, in fact, we see a rectangle because there are equal number of spins at each position X, taken at each strength of the magnetic field. And the resultant thing, what we see, the resultant signal is proportional to the magnetization as a function of x, y, and z, if we take the third dimension into account, and we integrate over the directions where the magnetic field does not vary. So we integrate over y, this integral dy, and the z direction not shown, and we are left over with a function that only depends on the variable x. And that the mathematicians call a projection. When I was a student, I thought a projector is something that a slide projector does, or a movie projector does. That's wrong, this is not a mathematical projection. And so this is a mathematical projection, and if one acquires many from different angles. So here's the object now, if you apply projection from this direction, from that direction, and from this direction, which you can do by changing the direction of the variation of your field, which is called the direction of your field plane. Then you get several projections. And one can reconstruct images from such projections. Computer tomography, which means X-ray tomography, was exactly this algorithm. And Paul Lauterbur discovered imaging with this algorithm, while Peter Mansfield actually used a different algorithm to do that, and which is called today, is called phase encoding, frequency encoding. There is one more slide here. Two more slides. I now want to go back to signal analysis. We've discussed Fourier transformation. We've discussed the fact that we measure a free induction decay, and here is actually the equation how that can be decomposed into a sum of rotating waves. You know that integral sign actually means is an old-fashioned S. S for sum, and that calculator Gauss introduced that as an old-fashioned S in the old Latin script, and stands for sum. So it's a sum really of different waves, rotating waves, e to the I omega t, and different amplitudes, and that's S of omega. So that's how one describes this signal. And the inverse, in the inverse Fourier transformation just means I now solve that for S of omega. So I plot S of omega here and omega along this axis, and resolve S of omega over spectrum. So all there is to it. There's a decomposition into rotating waves. And this actually is the signal of Fourier isotropy, natural Roberts, and natural Roberts solution. And that's the NMR spectrum of the natural Roberts solution. Now, if you look at the relaxation signals that one measures, you can also describe the relaxation signals. For those that like math a little bit, you can see the similarity. The signal is the sum over now decaying exponential function. Here is I omega t, that's a rotating wave. Now I have simple decay functions, and these are the amplitudes, how I sum them up. And one can also say, well, I can invert that and figure out what is the distribution of relaxation time. That's the distribution of frequencies, that's the second. So S of 1 over T1 is here, and then it's the logarithm of the relaxation time here, of T2, and that again gives me a distribution which is discrete and has peaks in many cases. It's sort of like a badly resolved NMR spectrum in itself. And this is the chemistry, and this is the physics. And people read these distributions of relaxation time and learn from it the four-size distribution of rock filled with a fluid or the Crossman density of rubber. And and other material properties. So there is a very interesting similarity. This is a new type of NMR, actually it's not new, but looking at it in that way is new. It's only something that has really developed in the last 10 years. And it has enriched magnetic resonance spectroscopy tremendously by drawing a lot of the experience people have collected in spectroscopy. What the chemistry community has been doing with two-dimensional NMR spectroscopy, that people have come up with two-dimensional NMR maps that correlate distribution of relaxation times T1, the distribution of relaxation times T2, and distribution of the fusion coefficients in two-dimensional and three-dimensional maps that only address relaxation information and physics information of material. And we will mention that also as we go along, so you know sort of the most recent approaches and there's a tremendous wealth that is there in magnetic resonance. This is the chemistry side, that's the physics side, This is the medical. Medical side is a form of three-dimensional spectroscopy. What people do in medicine is actually they replace the frequency axis with a position axis. So here's an image of capillary filled with water. And it's probably hard to see. It looks like a scattering diagram of an hexagonal method from X-ray. You see the hexagonal pieces. You can see 1, 2, 3, 4, 5, 6, and one in the center. And this is very reminiscent of X-ray scattering. In fact, there's a theory behind it that you can find a theory of scattering, of diffraction to NMR. And the Fourier transformation of this, the Fourier transform is the image. Now in X-ray you can't do that because you don't have the phase-sensitive information. You have the magnitude. And because you have the magnitude, you lose the phase. You can only look at the autocorrelation properties in X-ray. So you don't get the position of the scattering sectors, you only get the distance and completeness. So there's a beautiful relationship with imaging and scattering, and in fact diffuse scattering, but this is far beyond that scheme. I would like to, or that course, I would like to address that the transformation from the decay function to the distribution of relaxation times is often called inverse Laplace transformation. It's really not an inverse Laplace transformation. It's a solution of a Fredholm equation of the second kind for those who do math. And it only has to do with the fact that the Laplace transformation would require 1 over T2 to be a complex number, but it definitely is not. It's a real number. So there's a slight misnomer. It looks like it's an inverse Laplace transformation, but formally it's not, and this is why I also put the photo here of Mr. Fredholm. But Laplace is a contemporary of Fourier, both French mathematicians. They didn't like each other very much, but they addressed similar problems. The very last item to mention is a component analysis. When we analyze NMR spectra, we have these distributions of frequencies. We have peaks in here. We can group them typically into multiplex. This is what chemists say, how we know this. And then you integrate them, and from the integral you get the relative number of spins. So for example, if you have 3 spins in here, there are 3 spins, 2 spins in that chemical group, 1 here, and 1.16 is something, some measurement error in there is probably also 1. And you can learn how much the different, how many protons the different chemical groups. You'll see that next time, okay? Tomorrow we'll go more detail. I want to mention when you have a fluid in a porous medium, you get that type of distribution of relaxation time, which is similar to a spectrum, except it only has 2 peaks. You can also integrate the peaks and ask what do you learn from it. What you actually learn from this is that here you get the amount of fluid that you can extract from the porous medium, and here you get the amount of fluid that you cannot extract from the porous medium. So suppose you have a piece of land that has oil and you want to recover the oil, then this is the oil that you can sell and make money with, and this is what you cannot sell because you can't extract it. So it's a very valuable information to some people. Okay. And so there is a component analysis aspect to Fourier NMR spectroscopy, chemistry, and distributions of relaxation time, which is the physics. And with this, I want to finish that one chapter. I do have a few minutes left to address the next chapter, and I need to use that time. But do we have questions for this part of the course? Yeah. It's different in certain aspects because the only visualization, we don't need the very homogeneous field, but you need more presentment. And so that time between the radio frequency constant and the recording from the first data point that leads to the very short because it is in the very complex. Some people often don't use these high-field lines because they don't have any exposure to worry about it, and they want to see signal decay. And for that, they can work with them. So I'm really happy depending on the information of various types of big magnets within the different versions of the pressure in the composition. So the small molecules can work with the
machines. But typically one uses for sensitivity and chemical shift dispersion the big machines. The chemists, Mr. Physicists don't. Other questions? Okay. So we'll get out here and what do I have to do? Well, let's solve it for you.
This is the wrong one.
I need to go to number 3. Okay, now the chapter, and I think you have also received that part of the chapter, and you'll probably get scared when you look at it. It looks pretty complicated, it has a lot of math in it. But I will only go through pictures and explain you the contents of the math. I will not go through the math because it will take forever. We don't have that much time. But I want to guide you through the concepts, a way of saying, you know, let the mathematicians do the math. Let us figure out what they really want to describe with him. And this is what I want to explain to you. And I want to explain to you the underlying principles of spectroscopy. The information of spectroscopy is there because the spins interact with something. Okay, the first interaction, what the spins do, the magnetization doesn't interact with the magnetic field. This is why we can observe NMR in the first place. But then they also interact with each other. There's a spin-spin interaction, which gives rise to the J coupling, as the chemists know very well. But we also have a coupling through space, which we call the dipole-dipole interaction, which really makes solid-state NMR so difficult. This is why we use magic angle spinning. So once we understand a little bit about the spin couplings, we learn how to read NMR spectra, and we know why we have to do magic angle spinning if we want to do solid-state. So why I want to, put the burden on you of going through this somewhat complicated chapter is that you at least get an appreciation for these reasons and the underlying physics behind it. And the first part is that we want to understand what does coupling mean. And this is just the part sort of how a mathematician looks at coupling. I mean oh yeah, I have to put that up here. We look at spins. There's the spin, okay? The spin is nothing but an angular momentum that relates, is proportional to a magnetic dipole. That's what this equation says. There's an angular momentum, and the angular momentum is quantum mechanical, so it's a spin vector, and there is Planck's constant in the general magnetic ratio. So it says the spin is proportional to a magnetic moment, something we've discussed before. So it's a vector. A vector means it's a quantity that is oriented in space. You can rotate it, like a finger of a clock. So it has an orientation. It has a magnitude and a direction. So a vector typically in space has 3 components. Here's a vector, okay? So it has 3 components, so everybody knows. Now, if a quantity couples, interacts, you interact with somebody, you need an interaction partner. So it's 2. Minimum is 2 for an interaction. Now the question is, how does a mathematician describe an interaction? An interaction is described in terms of a multiplication, a product. Now a vector can interact with a scalar or with another vector. Typically it's a vector interacts with a vector. Equal, similar quantities interact with each other. So you have to describe the interaction of a vector with a vector. So 2 quantities that have a magnitude and a direction. And that is a general form of interaction is described by multiplication of the spin here, and the vector is the interaction partner, and that describes the type of interaction. It's a coupling mechanism. And the coupling mechanism is described by a matrix. I hope, how many still know how to multiply a vector with a matrix? Yes, you do? Okay, cool. I'll make a stop now. I usually have to explain in detail. So, here's a matrix, a 3x3 matrix. And what you do is you take that vector, flip it over here, and multiply these pairwise and add them, right? And then you do the same thing and multiply this one here with this matrix, and as a result you get a number. And that number is an energy. It's the interaction energy. How strong do you interact? Big energy, weak interaction, small energy. That's all there is. Now we have to figure out what type of interactions can a spin have. And the interactions a spin can have is what we call the Zeeland interactions, and the spin, this is the spin, interacts with the magnetic field. There's a chemical shift, this is the applied field. The chemical shift, which we want to measure in chemistry, that is the interaction of the spins with the magnetic field produced by the electrons surrounding the nucleus, the shield. Then we have the radio frequency excitation. We have to have an interaction of the spins with the applied radio frequency field, otherwise we couldn't do a 90-degree pulse. We have a quadrupole interaction, which comes in for certain nuclei that have a spin quantum number larger than 1/2. And then we have the dipole-dipole interaction. We take two magnets through space. And you know when you put two magnets close to each other, you feel either attraction or repulsion, depending on what their orientation is. And there's a third type, the last type of interaction is the indirect coupling. Again, you have two spins, but now they're connected by chemical bonds. And the magnetization of that spin polarizes the electron orbitals through the chemical bonds, and that spin senses through the chemical bonds the orientation of that spin. It's called the indirect spin-spin coupling. So we have the indirect coupling through the chemical bond, the direct coupling, the dipole-dipole interaction. And here I've given rough numbers, very crude numbers of how strong these interactions are. And the strongest interaction is a Zeeland interaction. This is for 100 megahertz spectrometer. Hardly anybody uses it anymore today. This is an old-fashioned chemical shift, maybe 10 kilohertz, depends on field strength and nucleus. Radio frequency excitation, 100 kilohertz, pretty strong radio frequency field here. Quadrupole interaction could be 10 megahertz, very strong, very difficult to measure quadrupole nuclei. Dipole-dipole interaction for protons and solids, 50 kilohertz, sometimes 100 kilohertz. Makes life very complicated. And the indirect coupling, 5 hertz. Weak, maybe 10 hertz. Very weak, very small. Again, hard to measure if you don't have a good instrument. So these are the interactions we have to deal with, but I see that my time is up, so I cannot go through those. But examples that we will address next time is we start with the dipole-dipole interaction, and we will learn that these interactions are anisotropic, which means they depend on the orientation of the molecule in the magnetic field. And in liquids, that doesn't play a role because the molecules move so fast that the NMR can only see the average of the molecule it sets. It doesn't see the orientation. But in solids, the orientation plays a role. And that is a blessing and a pain. It's a blessing because we learn about the orientational distribution of, let's say, chemical groups in spun fibers, how well are the molecules aligned in the fiber. And it's a pain because the dipole-dipole interaction is there and spoils our NMR signal. So we have to learn how to live with it, and we will talk about this next time. Any questions? No? Maybe when the camera is off? Thank you.
For the second course, participating in the second course should come at 2 o'clock. 2 o'clock you should be here. Thank you.